Thank you. It's wonderful to be here. It's been a wonderful conference so far. I really have enjoyed the talks and the discussions. So in the program it says I was going to talk about super cameras, but I changed my discussion based on the interests of the group here. Let's see if, there we go. So I want to talk about snapshot compressive imaging, which a lot of you have been working on in various forms. So one of the most fundamental problems in imaging is that we have a multidimensional data cube, like the hyperdepth data cube that Professor Arce talked about yesterday, but we only get to make a two-dimensional measurement. So we have to project the multidimensional space onto two dimensions. So this problem comes up in many different environments. Conventionally, people solve it by measuring slices of the data cube in sequence. But if you do that, of course, then you've sacrificed a dimension. You've sacrificed temporal resolution to get the three-dimensional data cube. But with compressive coding strategies, you're trying to implement something like code division multiple access. You're trying to encode each of the planes of a data cube onto a code that you can then analyze to separate the planes out from a single two-dimensional measurement. And so this figures from a review article that I wrote with Xin Yuan, talking about the general problem of snapshot compressive imaging. You have the problem after you've made this projection of how to estimate the data cube. At first, people look primarily at convex optimization as a strategy for doing the inversion. So in point A up here is the ideas of using L1 regularization or related strategies for taking the projected data cube and knowing the mass that were used to code the data planes, reconstruct the full data cube. But of course, in the last several years, these iterative algorithms have been replaced by neural algorithms. I saw on the Discord channel, people were talking about the difference between deep learning priors as a reconstruction method as opposed to end-to-end training. So, example of you could use end-to-end training, or you can use the structure of the network itself as a prior to try to do the reconstruction. And all of these methods in various ways and forms have been tried and gotten various levels of success for doing this inversion of getting a three-dimensional space from two dimensions. So the basic math behind this is kind of similar to all of these compressive tomography problems. This is a list of this basic strategy has been applied if the high-dimensional data space is a hyperspectral data cube, if it's space, time, two dimensions in space and time, if it's depth, if it's a fully volume kind of reconstruction, you can have polarization images. This is basic strategy has been applied with, there's three basic forms of tomography with optical fields. There's projection tomography like X-ray tomography. There's diffraction tomography like compressive holography. And then there's coherence tomography with statistical fields. All of those different systems have been implemented in various ways and shapes and form with the same basic mathematical format and the same basic reconstruction algorithms. Recently, Professor Yuan and I have just submitted another paper, and this paper is submitted. We haven't posted it anywhere yet, but I was going to talk briefly about it. I think one of the most interesting things is as we've shifted to neural estimators, the basic forms of the code that might make sense are evolving. Of course, this is a beautiful figure from the group here on the idea of coding the planes. You can think of this, the basic problem you have is that you're going to measure this G, some measurements. You have an unknown image F in a high dimensional space. And so normally you're going to make some just fixed physical projections. But with the coded aperture strategies, you apply some kind of coding structure that is a high frequency modulation. And the idea is that by the high frequency modulation in the data planes, you're going to alias high frequency content into the measurements. But with the emergence of neural estimators, the idea of convex optimization, which is kind of well adapted to these high frequency coding, may not be the best strategies. So in this paper with Professor Yuan, we've looked at things like here, we're going to take high resolution, low frame rate images, and then low resolution, high frame rate images, and combine those to estimate the data cube. And this particular paper compares those strategies with the same level of compression. But basically, there are many ways to consider sampling this high-dimensional data cube. The thing that the neural estimators allow you to do is, in these systems with the coding structure, the images are pre-registered. You don't have to think about how do you combine data from systems where, the registration and figuring out how the images are correlated in the reconstruction space needs to be resolved. Whereas with the neural estimators, taking images from disparate sources is a relatively easy thing to do. So this is another paper that we have that introduced a strategy for addressing this problem, what we call physics-aware transformers. So transformer networks are combined convolutional neural networks with more globally connected networks. And so what the global connections allow you to do is recognize features in the image that allow you to do some kind of processing. This particular paper, this is physics-aware transformers because we find the epipolar lines that relate the different images. So we use a physical structure of how we think the images are related and then apply local. Normally if you use a transformer network, you could get a very large neural network that might be difficult to train, but by finding the local regions and feature regions that correspond, we're able to combine data from multiple images. The main thing about these kind of algorithms is traditionally when you have multi-frame data from multi-array camera data from cameras, you use relatively naive strategies for registering the images and combining data from them. Here, the images are projected into a feature space with known geometry related along the epipolar lines, and transformers are used to combine the images and re-estimate the images from feature space rather than registering the images and combining them in the local space. And so, an example of what we do with these systems is we have this monochrome, high resolution, low frame rate image, and then low resolution color images, and we combine those to generate high resolution, high frame rate color images. Amazing things you can do with these kind of networks, by the way, because they're not really related by a sort of physical structure. We can do things like we take a near-infrared image and a visible image and combine those to estimate an improved visible image. The reason to do this is that the near-infrared images are less attenuated by the atmosphere, so we see more texture in panoramic images, and we can use the texture of the near-infrared image to create an improved high-resolution image. So in this paper with Professor Yuan, we've compared this CACTI, the CASI-like temporal encoding, with the transformer networks to reconstruct high-resolution video. And to be honest, the results vary based on kind of the structure of the image. That both of these perform kind of very similar. But the interesting thing is that there's differences in the physical implementation. And as we think about how to create these kind of sampling systems, we want to balance the algorithmic approach with how easy it is to do something physically. And so this array camera, multi-dimensional sampling, actually, the cacti and these interlaced coding strategies are well adapted to sampling the kind of images that you want, but they're not easy to build in a line, whereas in this case, for the array camera imaging, we build a small camera array with different color filters on each. We have a red, green, and blue and a clear channel on the array, and then we it's not really clear here, but this is like the red, green, blue, and monochrome image, and then this is the fused high-resolution image. If you go to the paper, this looks a little better than it looks here, but. And for me, where this gets really interesting for these kinds of strategies is that one feature of a CASI-like encoding strategy is that you kind of sample with uniform density over the reconstruction space. And in most cases, that's not really ideal. And you find that across the board with array camera applications. We make, for example, high-resolution cameras where we combine data from a bunch of narrow field cameras and a wide field camera to create a high resolution image. In most cases, we don't really want uniform sampling. Like along the horizon, we'd like high resolution, and then as you get into the sky, we might want lower resolution. This is also a common feature of these multidimensional sampling problems, is that different regions of the hyperspace may require different sampling density. So these kinds of strategies we can use, for example, to have like the monochrome or coarse spectral resolution in some of the cameras, and then high resolution spectral sampling along in certain feature spaces, and we get kind of a more flexible strategy. And I guess one point about this is that neither of these strategies that I've pointed out here, cacti or this array camera, is necessarily ideal, but there's a very large sampling space to you can think about combining these sampling strategies in a variety of ways. And then with these neural algorithms, we can estimate data from this very irregular multi-scale or heterogeneous sampling in ways that would be very difficult to estimate with a conventional L1 type optimizer. Okay, so that's kind of a background discussion of compressive tomography or multidimensional sampling. What I want to talk about now is a specific problem that's kind of fun and cool. So this is a specific array camera processing thing. And so this is a picture I love, because this is a picture from the last WACCI meeting that we had down in Chile. We were up at the European Southern Observatory. It was a great experience that we had at our last meeting. But you look at that system and you say, well, that's a really big aperture, so you're going to have high resolution. But I want to talk about, are there simpler ways to make a really big aperture? So the thing about this thing, of course, is it requires a building, and it has all that mounts and metal. One of the things that we've been working on is we work a lot with array cameras, and then we're interested in the problem of each of these cameras has a 5mm aperture, and we'd like to think about, as we look at these systems, can we create an aperture that is the size of the synthetic array of cameras rather than one of the cameras individually. Now, with incoherent light, that's actually not possible. That all those cameras would see the same image. But what I'm going to do now is kind of just give you a tutorial about what happens when we have this array camera with coherent light and how we can use that to synthesize an aperture. So actually, I'm going to give you, this is actually crazy because this is very basic physics, but it's not really well understood in the community. So I'm going to step back and talk about some cool things about coherent imaging. So this is just a very simple problem. We have an input field, and we're going to form an image of the input field through a lens, and we want to discuss how that process works. If we analyze it with Fourier optical analysis, basically we can analyze the impulse response for this system in steps that we know we have Fresnel propagation from the front plane, multiplied by the lens modulation, propagate to the back plane. That gets you to this real nasty thing that I'm showing in the middle here. So it's very well known that the impulse response of this system, this is this HR, this function right here, this is the impulse response, the airy disk that we're used to. So that's well known that the impulse response, you have a magnified version of the scene, and there's this impulse response. What's less well known is that there's these quadratic phase terms that are out in front of the impulse response. Now, if you have an incoherent imaging system, those quadratic phase terms don't really come up because you take the magnitude squared of the impulse response and those terms go away. But if you're imaging a coherent light, you see those terms. Now, if you look at kind of standard understanding people have, they say, okay, the impulse response is the Fourier transform of the pupil. And so that gives you, if you have a circular pupil, your impulse response is this airy pattern. And so people say, for a coherent imaging system, the passband, the transfer function looks like a disk, and all frequencies within the disk are passed, and an impulse creates this little airy pattern in space. Now, so if you form an image by this method, this is the kind of thing that you would expect. This thing on the left, this is the ground truth for two different images. The thing in the center is what happens after you image through an imaging system with this impulse response. Basically, you see the high frequencies are blurred out. The thing on the right, that's an assumption like if you block the center of an aperture, you have an annular lens and you would expect to build a high-pass filter. You'd see a high-pass filtered version of the image, and so you don't see the DC, you see a certain frequency band in the reconstruction. Now, this is, I think most of you, if you've studied optics, this is not a surprise to you. This is exactly what you think coherent imaging systems do. They have a square passband, they pass out all the frequencies. What's interesting is this is not how coherent imaging systems actually work. Because of those phase curvature terms. So you have these phase terms out in front, what the phase, you can think of the phase terms, so the phase term in image space doesn't really matter because you're going to measure the intensity of the field, and that's going to drop off. But there's this quadratic phase term that modulates the object. And what that means is that the passband depends on where you are in object space. So that the passband is shifting as you move across the object space with the coherent imaging system. I'm going to show you something now, which is, let's assume we have a plane wave. There's just a plane wave propagating toward a lens. Okay? Esteban, if I have a plane wave propagating toward a lens, what's the image look like?
A beautiful...
No, I'm going to image the plane. So I'm not focusing, I'm not going to focus the plane wave at the focus spot. I have some plane out in space where there's a plane wave. This is a really interesting question, yeah, because normally you think plane wave's coming, I'm going to focus it. But I don't want to Fourier transform the plane wave. I'm going to image out in space where it's a plane wave. Okay, so standard theory would say you would expect that to be 1. If you're imaging a plane where the value of the field is 1, the image should look like 1. But actually, it doesn't. It looks like this. If you have a plane wave propagating toward a lens, and you're not going to focus the plane wave. You're not looking at the image plane at the focal plane. You're taking some plane out there in the plane space and focusing it. The passband goes like the magnification times the aperture, and so what you would see is a disk where the size of the disk depends on what is the magnification of the system. Now, if you have like a microscope where the magnification is less than 1, then or you have a microscope, the magnification is large. So if you have a microscope, you're going to magnify it large. Then those quadratic phase terms turn out not to matter, and you would see a uniform. If you have like a microscope slide with uniform illumination, you're going to see uniform. But if the magnification is small, like in a remote sensing system, you're going to see a disk that's proportional to the magnification times the aperture. So actually, you're trying to image a plane out in space, and if your magnification could be like 1 in 1,000, your disk is going to be 1,000th of the aperture size. So what that means, if we repeat this imaging, we're imaging a chirped field here, the same kind of chirped field we were looking at before. Depending on the magnification, you're going to see, you don't see 0 out here. This is where the passband should be 0 from the original idea. But what you see is actually low frequency version of the high frequency field that's out there. There's high frequency images out there, but you're seeing it's aliased into a low frequency, or it's filtered into a low frequency band. And it depends on the magnification of the system, how much you're going to see. Interesting, like if you try to image an object, this is images of the object for different magnification aperture parameters. You see stuff like a plane wave. You see a disk that's only of the aperture size times the magnification. If you have an actual object, there's high frequency components out at the edges that then can get into the passband because they're modulated by this chirp frequency. What this means is not really all that surprising if you talk about what I'm telling you, but the passband of a coherent imaging system, so the passband of a coherent imaging system has a width that is 1 over lambda times the F number. So the frequency range that you can pass in an optical coherent imaging system goes from minus 0.5 times lambda 1 over lambda F to plus 0.5 times lambda over F. But the position changes depending on where you are in the image plane. And what this really means is that if you have a remote object and you image it with a coherent imaging system, that's a low-pass filter, but it's a low-pass filter with the center being the light that's propagating from the remote objects toward the center of the lens. So a plane wave, most of the light, if it's a very big plane wave out in space, most of that light's not really propagating toward the lens at all. So the center of the passband, wherever you are in the image field, is the light that's propagating toward the center of the lens. So this is, in some sense, really trivial stuff, but I would say not very well understood in the community at all, and it has profound implications for this idea of aperture synthesis. Because you want to ask, well, what happens if I move a lens? So if I have an object, each point in the image plane is seeing a part of the passband of the object. Now, if I move a lens, then by moving the lens, I'm going to be seeing the passband is going to shift in the image plane, so I'm seeing a different part of the Fourier space of the object just by moving the relative geometry of the lens, the camera, and the object. Okay, very cool thing, of course, because normally with an incoherent system, you move a lens, you're getting the same information, but here, just by moving the lens, we can scan through the passband or scan through the Fourier space of the object. If we take a mathematical analysis of this kind of thing, so we have this idea that the thing we measure is this quadratic phase term multiplied by the actual object field distribution with the impulse response. We can take that quadratic phase term and expand it in the shift. We're going to this delta x, delta y, that's a shift in position of the lens. We expand out the terms in that. We say whatever we're measuring from the object, let's just take this phase term and put it into this is the image we would measure for some fixed camera position. And if we move the camera position, what you see is there's now a linear phase term from the shift of the camera. So this is this idea that the Fourier frequency is changing. So this is a basic model we can have for what is the real image of a camera as we move the camera. That we have the, whatever the object we're going to image times the impulse response, but with a modulation in object space or a shift in the Fourier space of the image as we move the camera. This kind of thing is the basis of Fourier tychography. So tychography is a strategy that goes back to the 1950s for implementing phase retrieval. Conventional tychography, when you talk about tychography, the word means it's like fold imaging in Greek, and what it means is that you illuminate an object and you move the illumination region of the object, and so you can make a bunch of measurements of the field scattered by the object by measuring local regions of the object. And then you're going to measure the magnitude squared of that, and so then you're going to have a bunch of data that you want to do phase retrieval on. Fourier tychography and tychography are kind of the same thing, with the only difference is Fourier tychography, you measure images of the object with the local limited regions in the Fourier space of the object. So you're going to measure an image from one region of the Fourier space, and then you're going to shift that region of the Fourier space around. You like to have overlapping regions to help with the phase retrieval problem. Normally, the problem we have in optics with coherent fields is that we're unable to measure the field itself. We can only measure the magnitude squared of the field. So we need to implement phase retrieval. This is a quadratic form problem. We measure the magnitude, the magnitude squared of a variable instead of the variable itself. In phase retrieval, there's a whole bunch of algorithms, all kinds of things you can do, but it basically comes down to you need to measure about 4 times. If you want to reconstruct n values, you need to make about 4 n measurements, and tychography tends to work, or phase retrieval tends to work pretty well if you oversample by 4 to 10 or something like that. Now, of course, I'm a compressive measurement guy, so I'm going to say that's completely unnecessary in a minute. But that's the baseline idea for phase retrieval. If you're just going to do it and it's a completely random field, you need to oversample by a certain amount. So in Fourier tychography, people measure these local regions, but they do it with overlap in the regions that they measure, and then they're going to use iterative phase retrieval methods to try to reconstruct the image. So now in the Fourier tychography community, this has been around for a long, long time, the ideas of tychography, but it became super popular based on some work from Changwei Yang's group at Caltech about 8 years ago, where they used an LED array. So they built a microscope, and it's kind of a structured illumination. So they illuminate with plane waves from various directions on an object, an image through a single lens. And basically, as you illuminate, you're modulating at different frequencies. You could say you're going to alias different spatial bands into the lens. And they build a big LED array, illuminate from a bunch of different directions. And so when you do that, modulation, so basically in that microscopic Fourier ptychography, there's no motion in the lens. You're just illuminating with a plane wave from a bunch of different directions. So you have this same measurement model, but you're getting the measurement from illuminating from a bunch of different directions. But of course, we're in the snapshot imaging community here, so we don't want to do this, let's illuminate with a bunch of LEDs. We want to build a system where we get the high resolution image from a single snapshot. And so rather than illuminating with a bunch of LEDs, we're going to build a camera array. And so now we don't move the cameras. We just have an array of cameras that look at the object, and each one of those cameras then is seeing a different region of the Fourier space of the object. Problem with the camera array is that Fourier ptychography normally makes measurements in the Fourier space that overlap. And here we don't have that. We're going to make measurements where we have a bunch of regions of the Fourier space, but we don't have any overlap. So it's like, oh my gosh, how are we going to solve that problem? Because the phase retrieval doesn't like that. So we did what people do. So first of all, we built this system. We put a spatial light modulator in for our object. So now we can put as many objects as we want into the system. And we have a laser illuminated spatial light modulator, and then we image onto this array. And now we have a bunch of data. We have to invert the data. So just to give you an idea, this is what the data looks like. So this is a object that we put on the spatial light modulator. And actually, we were doing phase-only objects. So the objects are presented in binary phase, either plus or minus pi for each point in the object. So now what we expect and what you see, of course, is that these are the 16 images we take of this object, and the images don't look the same. The reason they don't look the same is because local points in the image, as you move the camera, will interfere with each other and create different patterns. And so you see this kind of variation in the scale of the structure of the image from different points or different cameras. And so then we say, oh my gosh, how are we going to take these 16 images and turn them into a nice, well-formed, reconstructed image? And we do the obvious thing. We say, oh, I know what we'll do. We'll build a neural network. So what we did is we present a bunch of images. We know the images. That's our ground. That's our ground truth we're going to use in training. We take the 16 images in a stack, and then we put them into a U-net, with the residuals flowing through. And if you like this paper has been published, and the code for this stuff is online. And then we're just going to present a few thousand images and try to do the reconstruction, and that works fantastic. So here you go. This is reconstruction, ground truth, and what the downsampled image looks like. And on this screen, I guess you can't see the difference that much, but definitely you can see that the resolution is so basically we were able to get about 8 times in each dimension resolution improvement over what we could get from a single aperture in this system. So basically we were able to show that we can get resolution consistent with the size of the synthetic array rather than the size of the individual cameras. We wanted to show that that we weren't just doing like neural super resolution. So we trained networks that with different numbers of measurements. So if we do 4 measurements versus use all 16 cameras versus all 12, as expected, we are seeing more information from having the array of images, and so it was important to us to have the full data set for the reconstruction. Then we also did testing with resolution charts. For different images, we had to make sure that we had the kinds of style of images, but so this is like, we added some things that are kind of data sets that have bars and things like this to help with the training, but basically we were able to get high resolution. If we look at like what one of the single camera images look like versus the reconstruction from the array, we're seeing this thing that we've increased our resolution by this factor of 7 or so from having the array of imagers looking at the scene rather than one camera. We did a bunch of simulation of different sampling strategies. So we were interested. We know we're going to subsample the Fourier space. So one of the real interesting challenges, which to be honest is not at all resolved in this space. So we have the cameras. So first of all, one interesting question is, this is great. So we built a system that's basically a coherent wave imager. It's like a synthetic aperture, and we've encoded the wave in a certain way. We've used these array cameras to encode the data. Now, of course, we could just build like a holographic system with the same aperture. The advantage here is that we don't have to have a reference beam, and that actually greatly relaxes the level of coherence we can have. We can do LED illumination instead of laser illumination and get the same kind of reconstruction power. But then there's a question like, how did we decide what aperture size to use in the micro cameras? We could use big cameras or little cameras or whatever. And we don't really know the right answer to that question. That we're still playing around with it. We did a bunch of simulation of what if we used, random-sized apertures in different displacements. And what you see here, as long as the kind of coverage area in Fourier space was pretty similar, the results didn't really vary very much. Mean square error was not too different for any of the strategies. So these are reconstructions from a whole bunch of different strategies, and you can look at the PSNR and the similarity of the images for each one for different numbers of photons. Now, as is common in this kind of space, if we take multiple snapshots, so if we take the camera array and move it or move some illumination, so we reduce the level of compression, we get improvements in the SNR. Okay, so we were real excited about that, and this area is super interesting and powerful. I would say, first of all, so the nice thing about tychography is we don't need a reference beam. The other thing is that the image processing is all local. That because we're working in image space, we're not really drawing on correlations, across wide areas of the image, and so it makes the processing simpler. The fact that we're reconstructing kind of local regions of the image rather than having to optimize globally over the image as a whole. So there are a lot of reasons why the Fourier tychography coding makes for algorithmic simplifications. But I would say I think that this is a continuing area. There's many ways you could think about, because we're dealing with coherent fields, the point of the lens is not really to form an image. The point of the lens is to encode the field to enable phase retrieval and reconstruction. And so there's work in the meta lens community to say, well, first of all, these are coherent lenses. We don't care if they're spectrally dispersive and things, and so we can replace the lenses with meta optics or with diffractive optics. We can encode patterns then, and definitely things around PSF encoding and other encoding strategies come into play here. So I would say this is a very rich space. I mean, the number one thing that this shows is that for coherent imaging systems, it's a rich space for data encoding that we can use to reconstruct in a wide variety of ways, and there'll be continuing discussion, I'm sure, about ways to do the encoding. Now, we did this in a pretty friendly environment, right? We did this with an object at a known distance on an SLM, and we don't want to stay there. We want to take these array cameras out into the real world and work with random three-dimensional objects. So we've done that. We've gone and taken diffuse objects, for example. Now, with the diffuse object, the phase is random everywhere in the scene, but it's random in a fixed instantiation. And this actually is where the snapshot aspect of the reconstruction becomes very important, because if you change the illumination angle or you change the illumination wavelength, that phase will change in unpredictable ways. So, but in a snapshot sense, the phase of a speckle pattern is well defined. we've taken these diffused objects and tried to do reconstructions, and we've had various levels of success. We don't achieve the same we won't achieve the same level of fidelity that we're seeing with the fully coherent smooth object, but we're getting definitely like maybe 4x improvement in the resolution. One thing you do if you take an image from an array camera with a diffuse object, if you just sum the images on the camera array, you're basically summing over different phase instantiations. You're getting the equivalent of the incoherent image with a single aperture image if you sum, but without the speckle actually, so it looks a little better. This is a reconstruction with a neural estimator. This is what we get in simulation where we don't have any errors in structure or anything, which looks fantastic. And this one we did, so we trained the neural network we trained it with random shifts in the camera positions. So we trained for uncertainty, we get a little bit better reconstructions. And so this is detail of, first of all, the kind of the measurement image. This is a picture of an orchestra, but then this is a measurement image on the left, the reconstruction at the top, and the ground truth, or the fully simulated at the bottom. This is continuing work. We're doing all kinds of crazy stuff with these coherent array cameras. I didn't talk about it today, but we've done some work where we put these on telescopes, and we're doing some work on telescope arrays. And one thing you could do is like, well, maybe you don't care about the reconstructing the high resolution image, you just want to add sort of the resolution to your perception. And definitely there's a lot of data here, and one part of the issues are that you get sort of overwhelmed with the scale of the data you can have in these super resolved systems. But we've also been doing things like, for these diffuse systems, there's a lot of challenges in getting the phase from a diffuse system, but we've been, and this is something that Esteban, you'll be interested in, that we've been working with these miners in trying to do like standoff super resolution for mining applications. People, geologists walk around with the loop thing because they want to look at the flex in the rock to see how much material is. So this is some images of some, what is it, mebdelite, I think the copper bearing stuff that has these little flakes in it. And then you zoom in on details from the array camera, and you see, especially in these little speckle scenes, the exact kind of structure that we want to see to do the super resolution. And so one of the issues we're kind of having some fun thinking about is using the array camera not really to form a super high resolution image, but just to form a super high resolution, for example, of the specular flex that you might find in minerals. This has been great to be here and talk to you about this. And what I've shown, I guess, is that definitely it is possible to, with a coherent imaging system, to create a synthetic aperture across the size of the array. We're continuing to work on registration, calibration, sampling strategies in this space. Because we're doing snapshot imaging, we can do all kinds of things, I think, with extremely high resolution dynamic scenes. I think what you saw from Professor Arce's talk yesterday, LiDAR is a pretty unexplored space when it comes right down to it for computational imaging. And especially when you think of like automotive LiDARs, they're doing, between you and me, they're doing really stupid processing. They're point scanning the scene. We can imagine LiDARs that combine these kind of strategies to create much more sophisticated, and you could use LiDARs with LED illumination instead of laser illumination and do all kinds of fun things. But again, actually, the very fun and exciting thing is that this is one of many kind of applications that are enabled by the ideas around snapshot compressive measurement, using the basic same kind of algorithmic techniques to solve these kind of problems. So thank you very much.
Hello. Okay, we have room for questions, so don't be shy.
Professor Brady, you're at Stanford. I have a quick question regarding like the first part of the talk. I know like you are one of the these people that propose being calling multiplexing access, calling division multiplexing access for spectral imaging or temporal imaging, etc. and now like it seems like you're moving towards like camera arrays, and it seems like there's a trade-off. There's a trade-off in like increasing the operation size or reducing the complexity of the processing. How much do we rely on computers, and how much actually we deploy the optics? But still, I'm not sure like about the like swap. In terms of swap, still we have like a array of cameras, and we have to synchronize all of them. I don't know, like the amount of power required, etc. So, can you elaborate a little bit more on like these trade-offs in terms of like size, weight, and power between these two structures? Thank you.
Thank you. That's an excellent question. So the question is, how do you balance physical processing and computational processing or digital processing in design of these systems? So first of all, people are always like beating us up about like the computational load that we have in different systems. In my experience, nobody has ever lost by betting on computers getting better. You know, basically, if it's possible for something to be calculated, a computer can do it. And so, you know, the things that are going on with computational power now are astounding. I mean, crazy. Like this new NVIDIA Orin chip does 200 teraof operations per second on an embedded processor. You know, and if you go to like the NVIDIA, GPU arrays, you know, you can do, peta operations in a like in a desktop machine. Computers always get better. So usually when we design these systems, first of all, I have friends like Professor Arce and stuff, so I never worry about the algorithm. I think I'll go ask somebody how to do that. Now the one thing is, like when you build a physical system, and you start to align things and you make it better. Maybe you make it like 2 or 4 times better by aligning stuff, right? You build an algorithm. First time you get the algorithm to work to where you're like, say, the algorithm is like I like it. Typically, the algorithm gets like 10,000 times faster, right? As you start to get into working with algorithms, you can always make them much, much faster as you really get into them. So all that is to say, when I look at designing the systems, I'm not usually interested in the algorithmic issues. What I'm interested in is the feature space of the measurement. So here's another thing about algorithms. Algorithms, like I'm showing you here, you can interpolate. Like if I have holes in the Fourier space, I have great confidence that I can interpolate into parts that I didn't measure. But if I want to extrapolate, I really doubt the ability of algorithms. So like if which is why like Cassie has these high frequency modulations that there's too many ways for the high frequencies to be uncorrelated to the low frequencies. And so we're usually interested in like what's the range of the Fourier space that we can show that the system is measured. And then if we get more general than that, we like to look at the principal components of the measurement. And then you get into like analyzing how do the features of the measurement space, in the ideal case, what you would want to say is I can look at the features, in a neural operator or in a principal component analysis or any strategy. I can find the features that are going to be present that I want to detect in the image. I can find the features that I want in the measurement space. I want to get some overlap between those. So that from a computational imager designer, I think that's enough. And then from the computational load point of view, I would just say that's somebody else's problem that people will figure out. But the level of right now, we don't have the capacity to generate enough data compared to what these new neural processing units are capable of processing.
Cool. There's more questions here.
Thank you for Master. So my question is about could you explain again about the importance of imaging optics?
I'm sorry?
Could you tell me again about the importance of imaging optics in coherent imaging? So basically, you can, for example, there's a setup for coherent imaging. So could you explain?
Professor Horisaki's question is, why do we need lenses here? Why couldn't we just measure holographically? The answer is, of course, we could. We could have a holographic reference instead of using the Fourier ptychography methods. I mean, the two issues are, number one, the coherence requirement on the source is greater if we try to get global interference. Because here, we only need pixels that are local in the image to interfere with each other. And that works for very incoherent sources, you know, because the path length differences are small. So we can use LED illumination instead of laser illumination. But then the second reason is just the you know, difficulty of presenting a reference beam to the signal as opposed to just setting up a camera array.
Thank you. And I have another question. So, as you said, future work is sort of calibration.
Yeah.
So what kind of as I said, approach do you use at this moment?
So one of the key challenges is that for this, first of all, the network has to be trained. We have an array camera. The network has to be trained with you know, the intrinsic and extrinsic parameters of the cameras. We need to know exactly where the cameras are to really not super high resolution, but let's say like 100th of an aperture or something. We would need to know the positions of the cameras. We thought that was hard. Well, number one, what we're doing right now is just trying to measure that very precisely to do some initial reconstructions. But beyond that, the cool thing about the neural processing is we can make you know, sort of multi-scale subroutines in neural algorithms. So we've been looking, I showed you data where we trained the neural network for some uncertainty in the camera positions, but we can also train a neural network to try to, from image data, calculate what the positions of the cameras are. So we're trying things where we do known illumination, neural calibration, and then just careful construction of the system to try to get the parameters. And the latest results are pretty good. You know, of just like knowing the camera reconstruction and doing the reconstruction. But I think in the long term, we would want to do a neural calibration to feed into the neural network to do the reconstruction.
All right, we have one question here.
Thanks, Professor Brady, for the talk. My question is about the slide that you said that you didn't know the answer about the sampling. I noticed that in the top of the slide, the patterns are like circular patterns, regular patterns. So usually for circular patterns, the density is 90%, and for regular patterns, you have a density of something lower than 90% for circular pattern. So maybe that is related. No, before.
Like this slide? Or?
No. After, sorry.
Oh, okay. This one.
Yes. So in the top, we have a regular circle.
Right.
Usually, in discrete geometry, the best way to packaging circles is 90%. So the strategies to solve the sampling problem involve design circular packaging, and in the bottom you have irregular circular packaging.
Right.
So the approach is design the circular, the centers of the circles, the correct positions, and they find the correct diameter.
Yeah.
So I think approaches related to packaging would solve the problem.
Yeah, very good question. Normally you would expect a more, so if you have a regular pattern, you would expect issues with aliasing that would be difficult to disambiguate. So if you go to a more irregular pattern, you would expect better performance. Now, this is kind of, here we have to recognize that we're also doing like a phase retrieval problem. And so we're undersampling dramatically because we should oversample by a factor of 4. So, but if you look, this is the number of snapshots. I guess this one is comparing like strategy 1 and strategy 6 there. Actually, strangely, like the kind of quasi-random patterns didn't work as well as larger apertures with, so basically, at least in our simulations, having some large aperture high resolution was better than having small apertures with low resolution. And I guess that could have to do with the level of multiplexing. It actually gets related to Professor Horisaki's question that if we have bigger apertures, so we need to have multiple apertures to be able to do the phase retrieval problem. And actually, there's a cost, to making the apertures bigger because the cost of lens apertures grows nonlinear as you increase the aperture. But you've done more physical processing if you have fewer and bigger apertures, and you have put less load on the computation. And it's not a problem, I think, with the intensity of the computation as much as the level of multiplexing. If we do less multiplexing, then the results seem to turn out better. So having fewer and bigger apertures, at least in this problem, was better than having random smaller apertures.
Great. We have one more question from Pablo, but I have to complement on this one. And so regarding the simulations, when you were showing these different approaches for the sampling, so how feasible is to have these circular apertures that close? So in simulations, you can show that how feasible is in physical ways.
Well, in our array, that was we're limited to something like this, but this is coherent fields. So actually, we're working on stuff where we replace the lenses with meta-optics and Fresnel lenses, and then actually the lenses can overlap, and we can integrate them on the same device.
Cool. Thank you.
My question is related with the idea of snapshot compressive imaging, since there is a limit of the amount of information that you can compress to a single shot, or if you consider like different dimensions or compressing a single shot, like the spectrum, spatial, temporal participation. What is your opinion about the use of deep learning across that limit that a lot of researchers are using deep learning to solve that problem? So what is your opinion related to that? Okay, the architecture is the good one, the learning is solve the problem or make information about it?
Thank you. That's a great question. So the question is, about what kind of levels of compression can we expect, and what is the role of deep learning in getting to the ultimate limits. So first of all, deep learning is obviously transformative to computational imaging. I think it's, but I wouldn't say like you see in these systems. First of all, deep learning doesn't work if you have like completely randomly coded data. Deep learning will not be effective. You need already to be. This is in these measurement systems, we have the trade-off between the dimensionality of the embedding spaces and the dimensionality of the data. So the embedding spaces are 2, 3, or 4-dimensional. So deep learning can be very effective about going from coded 2-dimensional data to expand to 3 dimensions, but it has to have image-like data to start with. And to get the data into something where a convolutional neural network can go and find features, you're likely to use conventional algorithms. So in most cases, I think you might find, like we did with the physics-aware transformers, we do local analysis from conventional image-based processing and then apply deep learning to estimate on local feature sets. And also with this tychography, we're finding that if we're already in something that's close to an image space, then deep learning is very effective. The thing about deep learning is it's extremely, extremely, extremely inefficient. There's no way that, the power of deep learning in some sense is just that all of this, the main problem is writing software. Deep learning is a way to automate the writing of software. But 100% guaranteed, if you were, God and could go create your own algorithm, deep learning is not an optimal algorithm. It vastly overuses computational resources to make the programmer's job simpler. So I would say, like, if you want to get to like the limit of like what's possible from a certain data set, first of all, like when you talk about compression ratio, it's a really very arbitrary thing. I saw a study recently where somebody had written that they had been able to do compressed sensing on a face database, and there were like 1 million faces, and these guys said they could make 10 measurements and reconstruct any of the 1 million faces. And they said this because their mean square error was low. So what that said though is not really, so they had 1 million faces, they trained a neural network, make 10 measurements and reconstruct any of the faces, and it looked beautiful. But what it says is that people are not that different. There aren't 1 million faces on Earth because 2 to the 10th is like 1,000. So what it says really is even though there's 1 million people, there's only 1,000 faces. And so compression ratio can be a very misleading parameter. But you're usually interested in like what are the limits of measurement, like what can be done from a certain data set. And there's a trade-off now between, the gold standard would be to go to maximum likelihood estimates, right? You have a certain measurement, and then you can use a maximum likelihood estimator to say what can be gotten from this measurement. But the problem with maximum likelihood estimates is that they'll only work typically if you're trying to estimate, less than 10 parameters. And so in image space, we would like to get estimates where we want millions of parameters. And so, people are doing amazing things with like, what are the limits of measurement of, like 2 point sources, how accurately can that, and with maximum likelihood estimators, people are able to show they can get amazing results. But at the same time, with neural estimators, people are doing neural super resolution, and neural super resolution is 100% real. We understand, like what I told you today, there's a certain band limit on an imaging system that would tell you the maximum amount of information you can get in a camera, but real cameras are very, very far away from reaching the sort of Shannon capacity limit. And given that that's true, they have embedded stuff, so you're kind of required now, if you have a camera, that your last step should be take your data and super resolve it with a neural estimator. That's a very real thing, but it's not really related to, it would be very difficult with a neural network, in my opinion, to talk about what is the real fundamental limit of information capacity or measurement. So, hope that.
All right, let's give a warm applause to Dave. We're moving to the next